In this video, safety radius of VTOL UAV subject to communication uncertainties will be introduced. Drones are now becoming increasingly accessible to amateur and commercial users alike. A safety air traffic management system is needed to help ensure this newest entrant into the skies does not collide with buildings, larger aircraft, or one another. This paper focuses on studying the safety radius of decentralized-control VTOL UAVs to deal with collision avoidance subject to sensing uncertainties including communication uncertainties. To formulate the safety radius design problem, a UAV model is introduced first, including the physical radius, the UAV control model and the speed limit. Then, a filtered position model is defined as follows by considering the velocity. Finally, an obstacle model is proposed containing the obstacle radius, the filtered position of the obstacle and the speed limit. For the sensing uncertainties including communication uncertainties, we have the following assumptions. In Assumption 1, the estimate noise for the UAV itself is defined. In Assumption 2, the broadcast delay and packet loss model is proposed when the UAV is receiving information from the obstacle. The relation among position, filtered position, and estimated filtered position is shown in the figure. Then we have some assumptions on controller. Assumption 3 expresses that a controller can make the filtered position distance always be greater than a safety distance in design phase when a design safety radius is given. Assumption 4 states that the estimated filtered position distance is always greater than a safety distance in flight phase. The safety distance is related to the practical safety radius. The objective is divided into two parts. The design phase objective is to determine the estimated safety radius which is related to the safety radius. The flight phase objective is to determine the practical safety radius to avoid collision in flight. In this paper, the method of collision avoidance is proposed, a principle that separates the safety radius design for uncertainties and controller design for collision avoidance. The safety radius design will take all sensing uncertainties into consideration, while the controller design does not take uncertainties into consideration. The separation theorem is shown as follows. As we know, the safety radius design for uncertainties and controller design can be separated when the estimated safety radius is equal to the safety radius. First, a necessary and sufficient condition is shown. The geometric significance of this condition is that the estimated filtered position distance will not decrease when the estimated positions of UAV and obstacle are close enough. Second, a sufficient condition is proposed. This condition has no velocity requirements for the obstacle, which is easy to achieve for the situations that the obstacle is cooperative. That is to say, the obstacle and the UAV are with opposite velocity direction when close enough because the right side of the inequality is less than 0. At last, another sufficient condition is stated, where the velocity of obstacle is limited. This condition applies to the situations that the obstacle is non-cooperative. Intuitively, the worst case is that the obstacle and the UAV are with the same velocity direction, so the velocity of obstacle must be less than the UAV. We have some propositions for the safety radius design. The design process is to find the relationship between filtered position distance and estimated filtered position distance by proposition 3, and the relationship between filtered position distance and true position distance by proposition 2. Finally, we have the safety radius design method in Theorem 2 to ensure no collision happens. As for the practical flight phase, we have the infimum of practical safety radius, which is shown in Theorem 3. The results above can be extended to multiple obstacles as well. Similar to the above, the obstacle model and objective is proposed to extend the conclusions to multiple moving obstacles. We have some new assumptions. Assumption 2 is replaced with a new one, where the broadcast delay and packet loss model is proposed when the UAV is receiving information from the multiple obstacles. Similarly, in the design phase, assumption 3 is replaced with a new one. It is worth noting that the filtered position error among UAV and obstacles is limited initially. Under some initial conditions, the UAV cannot avoid collision with obstacles no matter what a controller uses, such as this case. The introduction to the set is to make the problem completed. Under these new assumptions, the separation theorem is extended to Theorem 4. In the flight phase, assumption 4 is replaced with a new one. Under these new assumptions, Theorem 3 is extended to Theorem 5. The simulations and experiments are given to show the effectiveness of the design safety radius. During the simulation, 3 different scenarios are designed to show the proposed separation principle and the design safety radius. Different communication parameters are set. We can get the design safety radius by Theorem 2. The positions of UAV and obstacle at different times in case B of numerical simulation is plotted. In scenario 1, one static UAV makes avoidance with one moving non-cooperative obstacle is considered. As shown in figure, it should be noted that the filtered position distance is less than the safety distance after 5 seconds because of uncertainties. Moreover, the broadcast delay and packet loss model in assumption 2 is studied. The same input is given to the proposed mathematical model and the practical model. As shown in figure, for the UAV, the noise is bounded, obeying the normal distribution by Kolmogorov-Smirnov test. Therefore, assumption 2 is reasonable. Further, the distance between the UAV and the obstacle corresponding to 3 cases is shown in figure. Since case C does not satisfy the condition 3 of separation theorem, it should be noted that the estimated filtered position distance is less than safety distance. In scenario 2, one UAV makes avoidance with 3 moving non-cooperative obstacles is considered. These obstacles can avoid each other except for the UAV. Further, the minimum distance among the UAV and 3 obstacles corresponding to 3 cases is shown in figure. Similarly, the minimum estimated filtered position distance is less than safety distance because case C does not satisfy the condition 3 of separation theorem. In scenario 3, one UAV makes avoidance with 3 moving cooperative obstacles is considered. The UAV and these obstacles can avoid each other. The maximum velocity of the UAV is decreased to equal the maximum velocity of obstacles. As shown in figure, the distance among the UAV and obstacles still keeps greater than safety distance. Similar to the simulation, the experiment contains 3 scenarios. Different communication parameters are set during the first 2 experiments. In experiment, these parameters are got by system identification. A motion capture system called OptiTrack is installed, from which we can get the ground truth of the position, velocity and orientation of each multicopter. In scenario 1, one UAV makes avoidance with one non-cooperative hovering obstacle is considered. The distance between the UAV and obstacle keeps greater than safety distance. In scenario 2, one UAV makes avoidance with one cooperative moving obstacle is considered. Similarly, the distance between the UAV and obstacle keeps greater than safety distance. In scenario 3, one UAV makes avoidance with 3 cooperative moving obstacles is considered. During the experiment 3, the UAV always keeps a safe distance from the obstacles without any confliction. That's all. Thank you for your watching.